Today is the first exclusive webinar for Oasys Slope. I'm going to be your presenter for today, so my name is Zina Farouk. I am a geotechnical engineer by practice, and the webinar objectives for today are that you should be able to apply the analysis theory to produce designs, and also that you can present the analysis results for use in reports. So hopefully this would be a useful webinar for you practicality-wise. So the structure of the webinar today is that we're going to cover a little bit of theory, just briefly. I'm going to go through one or two case studies so that you know how the software works before we go into a live demonstration where I demonstrate setting up a problem, adding reinforcement, running a ULS analysis, and various other things. And also I've got a little nugget for you today where we're going to introduce to you the new Oasys Slope. The developers have been working hard to release a new version of Slope, which does a lot of different things and has quite a different interface. So I'm sure you'll be excited to see that. So to start off with, what is Slope? Slope is designed to analyze stability of slopes with the option to include reinforcement. It can also be used to analyze earth pressures and bearing capacity problems. Now, Slope is often used for soil and rock slopes, and the reason that this can be done is because it considers circular and non-circular slopes. And Slope has a lot of extra features. So, for example, you could add reinforcing elements such as rock bolts, soil nails, ground anchors, and geotextiles. There's an option for factoring. There are a number of options available, and it's all based on methods of slices and limit equilibrium analysis. So if I go into the analysis in more detail, there are three main types of analysis: the Fellenius and the Bishop's method for circular slips, and the Janbu method generally for non-circular slips. And depending on what kind of factoring you're using, what kind of slip circle you're interested in, for example, you would choose the method accordingly. There is much more information about these specific methods in the user manual, so I suggest you have a look at this if you are interested. It is important to understand the slope inputs because that gives you an idea of how the program works, and we're going to really familiarize you with this in the run-through. But very briefly, you need to give information about ground sections by layer of materials. So what you do is you type in the strata, you type in the material properties such as the variation of cohesion or the strength of materials. You give information about the groundwater profile, reinforcement. You can put external forces. It can be horizontal or vertical or tangential. And you need to put information about the slip surface in. So, for example, are you looking at a slip surface that already exists? So basically, you might be looking at a single slip circle. Maybe you just want to find the worst case slip, in which case you're looking at a grid. And there are different ways of specifying circles, going through a common point, just as a radius going out, or tangential to the surface. So depending on the type of analysis and the design you're doing, you have to specify that accordingly. It is worth mentioning here also that Slope has a number of features. So for example, you could even look into earthquake analysis and how slopes behave under earthquakes and various other things as well. So those options are available to the user. In terms of the output, there are two types of output. One is a very detailed tabular output, and this gives a lot of information about the slip circle. So this would be quite useful for any kind of design that you're doing. But we also have a graphical output. Now, the graphical output is really good for reports or presentations. It's very useful for helping the client understand where the failure is going to occur and how it occurs. So it just depends on your needs as to what you'd use, and especially with the graphical output, we'll really familiarize you with this in this particular webinar. So on to the case studies. With the case studies, we're going to present two case studies to you today. One which will show you how the program works on a large-scale project, but the other one will show you how the program is used in a different type of analysis. So hopefully both of them will be useful to you. Okay, so for the first case study, I'm going to briefly touch on the Nouvelle Ultra 30 Montreal, which was a massive highway built in Canada. It was completed in 2012. Now, Slope was used extensively on this. It was used to design the embankment material, and it was used for the earthquake conformation. So for this particular analysis, Slope was divided into zones with various shear strength characteristics. A number of failure surfaces were checked, And there was a higher factor of safety chosen for this project, which is 1.4, and that was due to the brittle nature of the champion clay. So this is just an example of the slope stability analysis that the Arup designers produced. As you can see, we've got some loading from the traffic at the top. We've got the embankment and formation from with various properties. As you can see, the grid has been chosen here, so they're looking for the worst case slope stability surface, and you can see this slip surface here is the worst case. As you can see, we've got marine clay and we've got groundwater as well shown. So it just gives you an idea of the kind of properties of slope and how it's used on a bigger project. But we are often asked about how it can be used with something a little bit different. Say, for example, if you're carrying out a basement impact assessment, if you're looking at retaining walls, how do you use slope? Well, Arup carried out an analysis on a proposed redevelopment, which was the enlargement of an existing lower ground floor and the construction of a rear basement. Arup required to assess the potential impact of the proposed development on the local surface water and groundwater environment, but more interesting for us, on the stability of the slopes in the immediate vicinity. So for the enlargement of an existing lower ground floor and the construction of a rear basement, why would you use a slope stability analysis? Well, by building the basement, the natural ground is altered, and the site within the area of previously worked ground, the site is within an area of previously worked ground, and it's also within 100 meters of potential spring line, which is underlain by a minor aquifer. So they had to look at the effect of the groundwater. The proposed basement will probably be extended below the water table, and it was also a local authority requirement. So with all this, the Arup engineers ran a long-term stability analysis of the clay, which was supported by underpins. Oasys slope analysis confirmed that the underpins alone would not satisfy the overall stability requirements. So for this particular analysis, what was done is that the engineers carried out a Eurocode 7 factored analysis, and they stated that the concrete ground-bearing slab could be incorporated as a prop at the base of the underpins. So if I go into this analysis, so as you can see, with the general parameters here are chosen as circular with a static analysis. And as you can see, we've got, if I go into the graphical input, you can see we've got a retaining wall here with the strata around it. So if I look at the wall itself, if I go to the material properties, you can see that the concrete has been given properties with full cohesion and no value of phi, so it's a completely drained analysis. And for the surface loads, we have a horizontal load representing the prop. And finally, it's worth mentioning that for this analysis, the engineers have carried out a Eurocode 7 design approach 1 analysis. So if I just carry out the analysis for this, as you can see, we're getting a factor of safety of 1 with the prop in place. So if I just choose the worst case slip surface, as you can see, we're getting a factor of safety of 1 around there. So that's acceptable, and that's because the prop has been input in. So that's, in a way, it gives you an idea of the way the program is used and where various things are. But to get a much better understanding, I think I'm going to start with the slope run through. So for the first stage, we're going to set up and run an analysis. So I'm going to do this absolutely from scratch. So what I'm going to do is I'm going to go into slope. And as you can see, when you start the slope program, you start up with a welcome screen. So you can open an existing file, you can go to the home page and find out a little bit more about the program. But what I'm going to do is I'm going to create a new file. So I'm going to click on OK. The model wizard starts up. It starts up with the titles in units. So I'm just going to call this slope run through. And subtitle simple analysis. So, for example, you could vary these subtitles based on what you're factoring or whether you're changing your groundwater levels or various other things. And the reason that this is important is because this shows in your tabular and graphical output. So it helps you differentiate between different types of calculation, and it gives information about your specific calculation. So I'm going to input the material properties for one material. The reason this is done is it gives you something to start off with, but it doesn't require you to fill in a number of things. So we've got a unit weight of 15 above groundwater level, and 19.5 below groundwater level, a phi of 20, and a cohesion of 5. So those are the embankment material properties. For the strata details, I've cheated a little bit and I've put some stuff in Excel. The reason I've done this is one, to actually show you the use of Excel in these types of programs, because you can easily just copy and paste between the tables, and what this allows you to do is, for example, set up something that another engineer could pick up, or alternatively have a base file where you know where everything is, and if you decide to change something, you have that logged in Excel. So I often like to do that for checking purposes. So we've got 2 groundwater. I'm going to look at 2 groundwater profiles today, an original and a raised, but for the purpose of the wizard, you only put 1 in. So I'm going to put original. Okay, and this is the slip surface definition. So if you remember, I mentioned that you could put a single circle in there, or slip surface, or a grid of slip surfaces. Now, I don't know. I'm doing a new design on a slope, so I don't necessarily know where it's going to fill. So I'm going to choose a grid. For the grid values, I'm going to put in something which ties into the geometry of my problem. So the grid's going to start at 25. I'm going to have this at minus angle of rotation minus 20. I'm going to have a number of points on the grid, and what these points mean is these are the points where the circle center could be calculated at. So it's important you have an adequate number of points, and it is also important that you extend the grid so that if the worst case circle isn't in your grid, that the program extends it out. I'm going to select define radii, and what this means is that the slip surface radiates out, and that's how the program calculates it. So I'm having initially at 1, and I'll increment it at 1. If I have, for example, an increment of 2 or 3, it'll be less accurate, but the analysis will be much quicker. And again, if I choose a higher number, so if I increment it at 0.5, then the analysis will take longer. Okay, so you can also choose tangent to surface or common point, if that's what you require. So finish that, and as you can see, we start off with something. So it is, as opposed to a blank screen, you have something there in front of you. But for the purposes of my analysis, it's not adequate. I want to put more materials in and more strata in. So again, I'm going to copy and paste through. I want to put another water profile in there. As I mentioned, I'm going to test it for 2 water profiles. So I'm going to call this one raised. Okay, I'm going to add that. Now I'm going to check this strata information I put in. So I've got a hydrostatic pore pressure distribution, which is what I require. I'm also going to add some strata in there. So the second one is going to be foundation. The soil, again, should be foundation soil, hydrostatic. I click on add. It's important you click on add before moving on to anything else. Otherwise the program doesn't save your changes. Bedrock, hydrostatic, and again, copy and paste. So this copy and paste option is available for different types of tables. So as you can see, we can put it into one of these types of tables here, or you can actually use it in these more complex tables. So, you know, it is useful to have that if you require it. And also you can copy and paste between slope programs as well. Okay, so I put the slip surface information in. I think we're ready to go, really. So I'll just check the graphical inputs to see that everything's been inputted as I require. So, for example, if has bedrock been input, okay. Yep, that seems great. Run the analysis. Okay. Great, so I'm getting a factor of safety of around 1, which is what I would like it to be. If I look at the single, if I click this off, so this is the plot all circles, I can see my single circle in there. And then if I go through the graphics option, so if I go to graphical output, if I go to plot all circles first, because I can't really see much from this, because as you can see, the legend here is going up to 300. So what I need to do is I need to go to graphics, graphical output, display settings, and have my maximum factor of safety around 2, maybe. And it will give me a better idea of what's happening. So as you can see, the worst case slip circles are the ones in red here. So it just gives you an idea of the kind of range that I'm getting out. And also maybe I want to present this to a client. So maybe I want to just label this up. So I might want to put in maybe the slip circle. So so as you can see, I've chosen the slip circle here. It's picked it up, and I can move this so that it picks it out there. So and I can move this pointer as well accordingly. There's also the case of maybe I wanted to put a soil label in. So this gives, for example, the name, and you can click in what you want, click OK, choose the soil you want to label. Again, using the edit label, you can move that label to somewhere which fits in a little bit better. And as you can see, you can build it up this way, so you can move things around and then you can have print it out. Now, with regards to printouts, I think it's worth me running through this. So, for example, with going into print setup, it's often useful in Slope to have a landscape print setup. And if I go to print preview, you can see that I've got this print preview here. The information that I put into the titles and units is here. So so it is important that I input that information in. And if I wanted to change how the printout views, then I would go to Tools and Preferences. I can change the actual information. I can change a company info or the page setup. So that's all available to you. And of course, a very important thing with anything that you run, and I should have really done this before I ran the analysis, is that you should save. So say, for example, I'm just going to save it at the desktop here. And that's done, really. So in terms of graphical outputs, we've covered everything. But I'm going to just open up the tabular outputs. I'm going to only show the summary results. Now, because there are a number of slip circles, a lot showing here. So as you can see, these are the summary results for a different set of slip circles. So there's quite a lot there to get through. And if, for example, you want to analyze it in more detail, you could go to File, Export, and export to CSV. So you could basically analyze it in Excel by doing that. But maybe with a tabular output, you only wanted to look at the worst case results. Slope will allow you to do that as well. So as you can see, we've only got the details for the worst case results, and that's shown here. So there is a lot available for designers, both in the detailed design and looking at the slope or the slopes, the failure surface, or alternatively with graphical outputs and producing it for reports. So that gives you a good idea of what's happening. So now we're going to go into designing the reinforcement and partial factor analysis. So before I go into this in too much detail, I am going to run through briefly what partial factor analysis is and Eurocode 7 analysis. Because what a designer would often do is they would run a ULS design and then, if required, put in some reinforcement and various other things. So it is important that the user does that. So there is a seminar available which covers this in a lot of detail. I've given this link here, which will be available afterwards, after the webinar. But here's just a screenshot from it, really, and we've got recordings of all our presentations, and we've also got the material. And the material that I'm going to cover today is just a quick excerpt of that. So briefly, Eurocode 7 is ULS design, or ultimate limit state design. It looks at the design effects, and it for the fundamental limit state equation, you basically want design effects less than design resistance. There are 3 design approaches in Eurocode 7, design approach 1, 2, and 3. We're going to focus on design approach 1, which is mainly used in, for example, the UK and some countries. There is a discussion with regards to which is best, and I suggest you have a look at approach to ULS design, the merits of design approach 1, because it shows that there are some benefits of using it, but it can be more onerous because you've got 2 combinations. And this is how something like slope makes partial factor analysis so easy, because it's just a click of a button instead of having to going through and factor everything. So combination 1 looks at factoring the actions, and combination 2 looks at factoring the materials. So generally, in a slope stability problem, unless you've got significant actions, you might find that, for example, combination 2 is probably going to be more onerous. So how to use Eurocode 7 how to apply Eurocode 7 to slope stability. It's covered in section 11 of the Eurocode 7. So if you are going to apply it, look at section 11. But throughout Eurocode 7, it is emphasized that slope stability should be looked at, because loss of overall slope stability or combined failure of the slope and structures should be the first thing checked for all structures and sites. And what this means is something that I'm going to cover in the following case study. So, for example, for retaining walls, if you don't look at slope stability, even if it's fine in terms of retaining wall design, it could still fail. EC7 applies to slope stability failures in a number of different situations, and there are a number of clauses which are appropriate to read. So you have to, EC7 will give you information about ULS design, SLS design, monitoring, and even the design and construction considerations. So we have an example courtesy of Brian Simpson, which is a dock wall analysis. So an excerpt from EC7 shows that there are lots of ways a retaining wall could fail. And what the designers had done is that they had looked at all the ways it could fail, basically from E to L, but they hadn't looked specifically at C and B here. So the areas circled in red are not shown and were not considered for this particular problem. So what happened was that a dock wall was designed with an anchor, but once the dock wall was installed, they found that there was a failure occurring here behind the anchor where this kind of red crack is shown. So initially a star wall analysis was carried out by the designers, and that was used to design the prop and various other things, and they found that their design was acceptable, and they went on to design it. But when you look at the slope stability analysis, you can see that a factor of safety of 1.189 is coming out. So this isn't sufficient in accordance with Eurocode 7. And so this is why there was a failure of this particular retaining wall or the dock wall. So a finite element analysis was run. I think you can maybe very faintly see the anchor or the back of the anchor here. And as you can see, this particular slip surface isn't perfectly circular. So what Brian Simpson did was he reran the analysis in slope with a non-circular slip. And as you can see, for this non-circular slip, a factor of safety of 1.11 was coming out. And actually, this was identical to the factor of safety from the FE analysis. So that was actually very comforting. And I felt it would be very comforting for slope users to know that you do get very accurate results out. Okay, so going into the program that we had set up, or the analysis that we had set up, if we look at the graphical output, again, we've got a factor of safety of 1.05. We should probably put some surface loads in. So what I'm going to do is I'm going to say I've got a surface load from maybe, let's apply something from, say, 0 to 20. Let's say we've got a distributed load around 10, say something similar to some kind of highway loading, useful and no. So let's have a look at the graphical input. Okay, it's going to probably finish here, so I'll say 0 to 15. I find it very helpful to check all my inputs with the graphical input as well. So if I run this analysis now, so you can see we're still getting a factor of safety of 1.02, so basically this isn't causing too much of a problem there. But now what happens if we run a method of partial factors? Maybe we want to do Eurocode 7 design. So I'll go to analysis options. Because we're looking at circular failure, we're going to looking at bishops, and variably inclined often shows to be the most accurate. So say I'm going to go for a partial factor analysis, apply. Method of partial factors. I'm going to choose EC7 and design approach 1 combination 2. As I mentioned here, we're factoring the material properties, and it's probably going to be more onerous in our case because we've not got massive actions affecting the slope. I'm going to click on apply. I'm going to run the analysis. Oh dear, our factor of safety is coming down to 0.817, so this is probably not going to be acceptable as a design, and we're probably going to have to maybe put some reinforcement in. So I'm going to double click on reinforcement here. So in the gateway, I've chosen reinforcement, and there are a number of reinforcement options available to the user. We've got ground anchors, soil nails, geotextiles, and rock bolts. But I'm going to go for a geotextile. Okay, and I'm going to have to choose multiple geotextiles really. So I'm going to go for maybe say 12, uppermost level 14, spacing 1, top layer 15, bottom layer 15. I'm going to stick with the effective width of 100, but I'm going to put the ultimate tensile strength to 100. This is not that high, so shouldn't be too difficult to design. I'm going to choose a factor of safety to apply to the reinforcement. So we've got the we've got a number of options here, and I'll show you how to input them also. But I'm going to use PS geotextile 120 years. Okay, and you must click on add, otherwise this isn't saved. So we've got the reinforcement in there. That shows here in the graphical input. It's also worth noting here that, for example, if I go to view, partial factors, I can actually change both the partial factors in terms of SLS or ULS design, or I could also change the material factors here. And that's what, if I wanted to, for example, maybe I have manufacturing details or there's something country specific, then I can change it accordingly and it's saved in there. Okay, so I think we're ready to run the analysis. If we analyze. Great, so we're getting a much more realistic, or we're getting a better over design factor for this specific problem. So as you can see, it's showing also which of these reinforcements are working the most, and where you've got redundancy. So that's also quite helpful for the designer, and it may specify that, for example, for these specific types of reinforcement, you may want to go for a higher tensile strength. Okay, so having done that, I also want to test it maybe for my raised groundwater profile. So for this specific profile, if I wanted to apply it, I'm just going to go through and change the strata. So I'm going to change this groundwater surface from original to raised. Okay, original, raised, original, raised. Okay, so now if I rerun this analysis, let me check with my graphical input, showing the water. If I now rerun this analysis, what do I get? Okay, the over design factor has reduced significantly. As you can see, we've got the groundwater profile going up to here, and it is a significant change. So it depends on how often this would occur as to how you might want to change a reinforcement. But say if I wanted to change it to soil nails, maybe I wanted to make the spacing lower. I'll increase this accordingly, and I would want to. You have the choice to calculate the bond strength here, so I'll do that. I'll keep this. I'll keep them at an angle. Outer plane spacing will be maybe 2. I'll increase the tensile capacity because otherwise it would be similar to running the geotextile. I'll make it maybe more significant. And I'll also factor the soil nails. Here we have the British Standards 8006, the most recent factoring option here. So this is the SLS, but I might go for factoring the strength here. If I apply this and analyze. So the reason I'm going through these different iterations is, as you can see, we're getting something much more acceptable now for Eurocode 7 Design Approach 2. The reason I'm going through this many iterations is so that you can see you can see what's happening really, and how this design is working, and how the designer themselves would go through and run iterations between different analyses. Okay, so I think that's pretty much our run through. So as you can see, I've set up something very simple. I've then gone on to factor it. I've gone on to design the reinforcement and play around with different groundwater levels and different things like that. So what happens, because our geometry was reasonably simple, what happens if you have a more complex geometry, or maybe you have a number of strata and you just don't want to go through and input it by hand, you don't want to put the coordinates in, it's too onerous. Well, what Slope allows you to do is allows you to import DXFs. So in terms of importing a DXF, I'm going to again start up the slope stability analysis from scratch. Okay, and I'm going to create a new file. This one I'll call import DXF. Okay, I'm going to again use the similar materials to what I had previously. So this time I'm going to go and repeat pretty much what I had done before, with a cohesion of 5. This time I won't put the stratum details in because we're importing the DXF. And for the grid details, what I'm going to do is I'm going to put grid information based on my new geometry. So this may not make sense right now, but when we import the DXF, it will do. So no angle of rotation is required. I'm going to put, because we've got a much bigger slope that we're analyzing here, I'm going to put more points on the grid, but they're going to be wider spaced apart, and this would be maybe to pick up the specific slope center of the slopes the failure surface. And once we picked up the center of that failure surface, what I'll then do is maybe I'll take a smaller grid and zoom in on it. So the initial radius should be 1, and the increment should be 1. So shall we have a look at what effect there would be if we don't extend the grid? I think that would be of interest. So I'm not going to extend the grid on purpose. Maybe I had forgotten to do so, or maybe I just wanted to pick up a certain area. So I'm just going to click on Finish now. And as you can see, we've basically got the grid there alone and nothing else. I'm going to import, so go to Air File, Import DXF file. I'm going to choose a DXF that was previously created. Okay, so I've imported the DXF data, so as you can see, they're shown here. But to be able to use it, I'm just going to go to Graphics, Graphical Input, and just check that DXF import is selected, which it has been. So now all I need to do is click on that specific line, which is of interest. So here we've got top of stratum, and if I click OK, I'm going to call this embankment. I'm going to click on this and I'm going to call it the groundwater table. So I'm just going to call this original. Okay, and I'm going to click on this and I'll call that, say, bedrock. Okay, so before going further, I need to put in more material properties as well. So I'm just going to copy and paste for this case. Okay, and as you can see here, we've got embankment soil. Okay, so I'll apply those changes, and bedrock, I'll go for bedrock and the bedrock as well and apply. In terms of groundwater, it's I think I didn't click on that correctly. So what I'm going to do is I'm going to go back to Graphics and DXF Import, click on this, go to Groundwater Table, Original, click on OK, and as you can see, that's now showing on there. So I'm just going to choose a hydrostatic profile. I think it's just applied as it is. Okay, that's great. So, so now I can run the analysis. And as you can see, we're getting a minimum factor of safety here of 0.684. So it's actually picked up the minimum factor of safety with this specific grid. But if I had chosen a grid maybe over here, it wouldn't have done. So I didn't need to extend this grid because I had chosen a coarse enough grid. But what would be a good thing to do now would be to actually zoom in on this. Maybe zoom in on this particular area and have a look at where this grid is occurring, and maybe have a finer grid here. So instead of having a spacing of 4 meters, having a spacing of 1 meter or 0.5 meters, and having a look at that. You might also note that this grid, you might want to pick up maybe a bigger slip surface. So if you wanted to do that, what you would do is you would go to general parameters, and under minimum weight here, you would type in something bigger. So because we've got quite a large geometry, I'm just going to put 10,000 in here and see what happens. So if I rerun this analysis, as you can see, we're getting a bigger slip surface out there as well. So that gives you an idea of how slope works, and it gives you a few tips and tricks as to what you should do to pick up the slope surfaces or the slip surfaces and various other things as well. So having gone through the run through now, I think we're ready to have a look at what the future holds. So in terms of upcoming slope developments, the developers are looking to make it easier to specify slope strata and materials, and look at groundwater flow and head boundary conditions for seepage analysis. So the results from the seepage analysis are going to be used in groundwater distribution. So in the slope stability analysis, this could be used by the method of slices. So currently slope doesn't consider seepage, for example, and now it will do. So that's a big change. Another big change is that you could actually rerun the similar slope analysis and compare it to an FE analysis. So the way it would work, for example, is that, as you can see, as with slope, it picks up the worst case slip surface. It picks up the range of slip surfaces, but it now looks at the movement of water as well, which it hadn't done previously. So as you can see, again, you've got these options available here as you normally would do. So this is quite a big change, and it will basically provide you with all the features that slope has and more. So we're quite excited about this, and we feel that this will be a big improvement and help a lot of users. So in summary, I've run through the analysis methodology. So now you should understand a little bit more about the limit equilibrium analysis of circular and non-circular slip surfaces. I've run through a simple slope analysis. I've also helped you look at how, for example, you would approach factor design in slope, and then go on to design reinforcement. We've looked at, for example, putting raised groundwater tables in, putting loading on the slope. I've then introduced the importing DXF feature, which would really simplify, for example, complex geometry or lots of stratas. And I've also introduced you to a very exciting upcoming development, which we're hoping to release over the next 6 months. It just goes for me to say that you can actually have a look at the slope tutorials. We're writing up one. Over the next month or so. So you should have a step-by-step tutorial available, and that could be accessed via the tutorial section of the product page. So on the product page, you can click on any of these video tutorials, and hopefully we should have a PDF tutorial available to you as well. Related webinars are available, so you can have a look at what webinars were there previously. And if you just want all of this in one place, at the bottom of the Oasys page is a link to YouTube. Type in slope on our YouTube page and you'll get up everything. We do also like people to contact us, so please feel free to email us or call us. We're happy to take any queries about the program, any queries about its use. There are also technical FAQs that you can look at. So thank you very much for your time, everyone, and I hope this was useful. Are there any questions?